Now, we were discussing about the biodegradation of polymer products. Now, let us discuss about the various factors which are responsible for biodegradation of such polymers. These factors, the most important factor is chemical bonding in polymers, that means nature of bonding, nature of chemical bonding. Chemical bonding I mean, say as I told, a primary covalent bonds and secondary bonds. It will be clear if we think of this polyethylene having this kind of bonding. This is the repeat unit of polyethylene. Here we find primary covalent bond between carbons, primary covalent bond between hydrogens. There can be other kind of bond, say having this kind of this is the repeat unit formula of polyethylene terephthalate. This is polyethylene, this is polyethylene terephthalate, polyester. This is hydrocarbon polymer, it is non-polar, this is polar polymer, this is polyester. If we compare the nature of bonding between these two polymers, apart from carbon to carbon bond, apart from carbon to hydrogen bonds, there are bonds like carbon to oxygen single bond, single covalent bond, and carbon to oxygen double bond, and carbon to oxygen single bond in the backbone chain. So, degradation performance of these two polymers are totally different. This polymer is considered as non-degradable polymer in the environment, this is a degradable polymer in the environment. So, we have to think of what kind of bond is present in chemical bond is present in those polymers, what kind of secondary bonds are present, what kind of what is the total quantity of secondary bond is present. So, that is related to solubility parameter of the polymer, solubility parameter. So, these are all correlated. The solubility parameter can also give some hints about the effect of this chemical bonding on solubility, on the polymer strength of the polymer and their degradability, etc. Then polymer structure. Polymer structure, if we again think of this two polymers, polyethylene and polyethylene terephthalate, the structures are different. So, their degradation phenomena is also different in these two polymers. Then what about the microstructure and morphology? Microstructure, it means that in the solid state these polymers normally the polymers are amorphous in nature, but there are polymers which are semi crystalline or crystalline polymers, means if there is long range order in polymers as is found in case of polyethylene, this is a semi crystalline polymer whose crystallinity can vary from 40% to 60% to 70% crystalline percentage, and the rest is amorphous. So, this is semi crystalline polymer. This can also be crystalline polymer if it is developed in the form of fiber. Similarly, nylon, that is also a crystalline polymer. So, that if that polymer contains crystalline structure, we say the microstructure is crystalline as well as their morphology. Then side chains. Now, there can be polymers like say PMMA, polymethyl methacrylate. Its formula is this. Sorry. This is substituent, or you can say side chain, or a polymer can have, so this is configuration wise, it can have a side chain or branch like this. So, that whether the polymer contains side chain or not, if whether the side chain is polar in nature or non-polar in nature, this is a polar side chain, this is a non-polar side chain or side group, etc. So, that also influence the biodegradation or degradation by microorganisms. Molecular weight. If the molecular weight is very high, again the degradation will be lower. So, molecular weight is also a parameter or a factor we must think of. Melting point. High melting point polymers, or the polymers which actually melt at very high temperature, those are not degradable very easily, that takes longer time. Whether polymers having lower melting point, lower softening range, they degrade faster. Similarly, the crystallinity which is related to this microstructure and morphology, etc. And let us think of other structural requirements which I have already pointed out, say polymers containing these ester groups, ether groups and peptide functional groups, they are degradable. Now, presence of branched hydrocarbons means side chains that slows down the biodegradation process. Particularly, the presence of a tertiary carbon atom. Tertiary carbon atom means this carbon polymer chain, this is the carbon atom. Now, this can be attached to groups like this. So, this carbon is called tertiary carbon. Now, if the polymer contains a tertiary carbon having no hydrogen substituted group, is highly resistant to biodegradation. Hydroxyl and carboxyl groups, presence of hydroxyl or carboxyl group along the backbone chain of the polymer like this, that accelerates biodegradation. Now, unsaturated aliphatic compound is more biodegradable than its corresponding saturated compound. That is why this polyethylene having this saturated backbone chain like this is not degradable, whereas if a polymer chain contains unsaturated bonds like this, other groups are there. So, if such type of bond is present in the polymer backbone chain, so such polymer will be degraded faster than the polymers having the saturated structure. Now, the order of biodegradation of polymers, say aliphatic polymer will be more degradable than polymers which are in alicyclic in nature than aromatic in nature. So, aromatic polymers are less degradable than aliphatic polymers. Similarly, a polymer if it is hydrophilic means water loving. A polymer whose surface can be weighted by water or which can mix up with water, etc. These are known as hydrophilic polymer. For example, say polyvinyl alcohol is a hydrophilic polymer. This is polyvinyl alcohol. This is a hydrophilic polymer. It dissolves in water, it is a water soluble polymer, this is degradable. Similarly, say polymer like this is again hydrophilic, polyacrylic acid, this is again hydrophilic, this is also biodegradable. Similarly, polyvinyl acetate, this is again biodegradable. So, these are all hydrophilic polymers, whereas polyethylene, say LDP or HDP, high density polyethylene, or polypropylene, these are hydrophobic polymers, these are non-degradable. So, hydrophilic polymers are more degradable than hydrophobic polymers. Polymers having low molecular weight is more degradable than high molecular weight. Polymers having lower melting point, lower softening range, softening point, then higher melting point will be more degradable. Amorphous polymers are more degradable than crystalline polymers. This is because these crystalline polymers are compact due to the molecular alignment. The free space in between the molecules, intermolecular space is less, where this water cannot penetrate or the chemicals cannot diffuse inside, or even the microorganisms cannot go inside the crystalline polymers, whereas amorphous polymers having more free space through which these can go inside the bulk of the polymer and that degrades faster. So, that is why amorphous polymers are more degradable or faster degradable than crystalline polymers. Now, effect of morphology on biodegradation, as I pointed out that morphology or microstructure, these are also influential parameter for biodegradation of polymers. Now, biodegradation of a water soluble polymer is a heterogeneous reaction. So, size, shape, surface area and surface texture greatly affect the rate of degradation of the polymers. Highly crystalline cellulose degrades at a much slower rate than that of irregular branched and non-crystalline starch. Highly crystalline cellulose means that cellulose molecules say it looks like this. So, these are all carbons. So, this is primary hydroxyl group hydrogen, secondary hydroxyl group OH, H. So, it contains anhydroglucose unit. It contains anhydroglucose unit. Now, that anhydroglucose unit it contains these hydroxyl groups, primary and secondary hydroxyl groups, as well as this oxygen atom over here. So, due to the presence of these hydroxyl groups, there can be intermolecular hydrogen bonds. So, if we represent this cellulose as ROH, now this ROH you can write other way OH, another ROH can be written this way. So, this oxygen and hydrogen can initiate this hydrogen bond. So, in case of cellulose there is extensive intramolecular hydrogen bonds. Now, these intermolecular hydrogen bonds present in cellulose that behaves like pseudo cross link. Bonds. So, pseudo cross link bonds means these there is intimate bonding between the anhydroglucose units of each anhydroglucose unit of one molecule with the other anhydroglucose unit of the other molecule. So, that does not help the polymers to be more hydrophilic, and that prevents biodegradation. So, that is called actually that due to that hydrogen bond, that cellulose molecule becomes highly crystalline. So, highly crystalline cellulose degrades at a much slower rate than that of irregular branched and non-crystalline starch. So, if the crystallinity in cellulose can be reduced by some chemical treatments, say we can say the regenerated cellulose. This is also cellulose, regenerated cellulose is also cellulose. This is prepared by, suppose this is cellulose ROH. Now, in one of the techniques of different regeneration processes, say this is one, say it is reacted with carbon disulfide and sodium hydroxide, it forms sodium cellulose xanthate. This is soluble. That means, cellulose can be cellulized, dissolved in carbon disulfide, aqueous solution of carbon disulfide and sodium hydroxide. It forms a viscous solution in water. Then, if it is put in acid bath, say dilute acid bath, say sulfuric acid, dilute sulfuric acid, cellulose will be regenerated. Now, this process of treatment of cellulose with carbon disulfide and sodium alkali and then reprecipitation in acid bath, it gives back the cellulose. In this case, the hydrogen bonds, the number of hydrogen bonds in that cellulose is reduced. Here it contains less number of hydrogen bonds, here contains more number of hydrogen bonds. So, this become soft and that is more hydrophilic and that is more degradable than the cellulose, which are the original cellulose molecule, original cellulose material. Lignin with cross-linked carbon chains with aromatic ring structure degrades very slowly. Now, lignin is a molecule that is a polymer. Lignin is a polymeric material. That lignin occurs in nature in wood as a matrix material, cellulose plus lignin makes the wood. That means, wood is basically made of cellulose and lignin, where cellulose is the fiber and lignin is the matrix, and this form this wood composite. This lignin contains some phenyl rings attached to aliphatic chain. Basically, these are the derivatives of phenyl propane unit, phenyl propane structure, and that is a giant molecule. Lot of linkages between such phenyl propane units and the molecular weight becomes more than 5 lakhs Dalton. So, that is the high molecular weight lignin, and that lignin when cross linked with carbon chains with aromatic ring structure etcetera, that also degrades very slowly. That is why not only that, this phenyl propane structure and it contains some phenolic groups. Due to the presence of phenolic groups, these phenolic groups are phenolic groups prevent oxidative degradation. That is why we see that hardwoods earlier, these hardwoods containing high lignin content, containing high lignin amount, have a high amount of lignin, say salwood. This is heavy wood, this is very heavy, density is very high, it is also very strong, and the salwoods were used as railway sleepers. Today railway sleepers have been wooden railway sleepers are replaced by steel sleepers, then concrete sleepers. Today almost entire railway track has been replaced with these reinforced concrete sleepers. Now, earlier this salwood, now that was remaining exposed to environment, open environment, outdoor environment, in contact with soil, in contact with air, in contact with heat, sunlight, etc. Still those are not so easily degradable, and the life of those wooden sleepers were very high. That is due to the presence of high quantity of lignin, which contains those phenyl rings and phenol units, which actually act as antioxidants or anti-degradants in wood. So, it is true that if a polymer contains lignin, that polymer will be stable, it will not degrade. So, that degrades very slowly, even it degrades, that degrades very slowly. And wooden furniture, the life of wooden furniture is so high because of the presence of lignin in wood material. Amorphous regions of polymers of partially crystalline polycarbolactones, like partially crystalline polycarbolactone film, degrades before that of crystalline regions by fungi. So, it has been established that a polymer, if it is amorphous, it will be degraded faster. Now, let us see the examples of polymers having hydrolyzable backbones, which can be degraded by hydrolysis. So, these are polyesters, polycaprolactone. This is also another kind of synthetic polyester made from epsilon caprolactone by ring opening polymerization. Polyamides having peptide linkage, links in proteins. This is peptide linkage which is present in proteins. Same linkage is present in polyamides or nylons, say nylon 6, nylon 6,6, or these are aliphatic nylon. There can be aramid, which is aromatic nylon. Now, aliphatic nylon degrades faster than aromatic nylon. So, these nylons are in general known as polyamides because of the presence of this amide linkage, which is similar to that of peptide linkage in proteins. polyurethanes and polyureas. Polyurethanes containing linkage like this, this is polyurethane linkage having nitrogen, oxygen along with carbon and hydrogen in the polymer chain. Polyureas etc. Polyanhydrides, polyamide enamines, polyamide imides etc. So, these polymers are degraded by hydrolysis. So, they are known as hydrolyzable polymers. So, again typical examples of hydrolyzable polymers are polyester, say polyglycolic acid, this is a synthetic polymer, polyglycolic acid, co-lactic acid is a copolymer. These are used as degradable and absorbable sutures. Now, after surgery, it needs to be two parts needs to be joined by stitching with sutures. Now, previously chromic catgut made of sheep intestine submucosa. This chromic catgut is not degradable. So, after surgery and stitching, when the wound heals, then it needs to be removed by a second surgery, which becomes painful to the patient. Now, today bioabsorbable, biodegradable sutures have been developed from this polyglycolic acid or polyglycolic acid, polylactic acid copolymer or polylactic acid, which slowly degrades within the body and the degradation products gets absorbed within the body without any hazards or toxic effects onto the living system. So, these synthetic polymers are very good biodegradable or bioabsorbable polymers, and after 7 to 15 days depending on the nature of wounds and nature of healing time etc. So, these polymers slowly gets absorbed within the body, and by that time wound heals. Polycaprolactone, this is obtained by ring opening polymerization of caprolactone used in controlled release of drug delivery system. Blends of polycaprolactone, aliphatic polyester and tree bark are used for horticultural seedling plant outs. Polyamides, in polyamides introduction of benzyl group, hydroxy group or methyl group that improves biodegradation of polyamides. Polyamide esters, these are ester amides, that means a polymer containing both amide linkage and ester linkage, which are both hydrolyzable, or amide linkage or urethane linkage, which are both hydrolyzable. So, polyamide ester or polyamide urethanes with long repeating chains that degrades at rates between those of proteins and synthetic polyamides. Polyester polyurethanes are also readily attacked by microorganisms and hydrolyzably degraded, and then the polyether polyurethanes, these are also degradable. So, polyurethanes can be polyester polyurethane or polyether polyurethane. Both polymers are degradable either by microorganisms or through hydrolytic path. Now, here are the structures of those polymers: polyglycolic acid, polyglycolic acid, lactic acid, polycaprolactones, polyether polyurethanes. They are having intermolecular hydrogen bonds. and polyamide in amines. If you look into the structure, you can understand why they will be degradable by microorganisms, or they will be degraded by the action of acids or alkalis through hydrolysis. This shows a scheme of reaction which occurs during hydrolysis of polylactic acid. This contains ester group. This is the reaction, how it degrades. Ultimately, this is the fragment, this is the products of degradation, this is one product. So, after fragmentation, this smaller small length species will be formed, which will be easy for the microorganisms to metabolize. Length of time taken to degrade polylactic acid in water. Some experiments were carried out. This is the reference of this work published in Polymer Degradation and Stability. At different temperatures, the onset of fragmentation. What happens during degradation? First of all, the polymers get fragmented into smaller lengths. After fragmentation, through hydrolysis of those hydrolyzable bonds, then microorganisms can perform at a faster rate. So, this shows the time period at different temperatures. Say, if you do the degradation or fragmentation at lower temperature, the time requirement is quite high, whereas if the temperature is increased, this fragmentation will be very faster, from 64 months to it has come down to say 2 days, around 2 days. And onset of biodegradation again at lower temperature, it is very long, as I mentioned that in high altitude area where the temperature is very low, sometimes sub-zero temperature, there even the night salt does not degrade. Forget about the degradation of polymer materials. But if the temperature is increased, the degradation is much faster, from such 123 months to 3.5 to 4 days time. This shows the decrease of molecular weight with time during degradation, as well as evolution of carbon dioxide due to biodegradation of the polymer. Now, here in this period of time, say 10 days, within 10 days time, embrittlement of the polymer to fragmentation it starts, and ultimately between 10 to 15, after 15 days, there it has been found that the polylactic acid was completely fragmented at 60 degrees Celsius temperature in compost condition, and you see the molecular weight has come down from 70,000 average molecular weight to almost 10,000 molecular weight, species of 10,000 molecular weight fragments. And it shows almost complete biodegradation, 100% biodegradation in 40 to 45 days time period. Polymer with carbon backbones, these are also degradable. So, I showed that polymers containing such degradable groups like ester, ether, amide in along the backbone chain is one kind, and other kind is the branched or side chains like this. So, we have discussed polymers of this type, where the degradable groups, functional groups say ester, ether, amide etcetera were present along the backbone. Here those such groups are present in the pendant groups or the side chains. These are say polyphenol alcohol. I have shown you the formula of polyphenol alcohol. Once again you can see that is this polyphenol alcohol. this polyphenol alcohol. This polyphenol alcohol PVA most readily biodegradable vinyl polymer. Initial biodegradation involves enzymatic oxidation of secondary alcohol group. This is the secondary alcohol group in PVA to ketone group. It is converted to ketonic group like this. So, it will break over here and form a ketone. So, fragmented polymer. So, ketonic groups, hydrolysis of ketone group results in chain cleavage. So, gradually hydroxyl groups is converted to ketone, then ketone groups result in chain cleavage. In case of polyphenol acetate, that degrades more slowly and degradation occurs through hydrolysis of polyphenol acetate to PVA followed by enzymatic oxidation and degradation. Say this is polyphenol acetate, this is the repeat unit of polyphenol acetate, you can write this way also, polyphenol acetate. Now, this is the vulnerable bond where it can hydrolyze forming this polyphenol alcohol and acetic acid. So, first this acetate group will be hydrolyzed followed by enzymatic oxidation and degradation of this polyphenol alcohol. So, because of this first step of hydrolysis, then degradation, it takes longer time or degrades slowly. Polyacrylates, polyalkyl acrylate and polycyanoacrylate generally resist biodegradation. Copolymers of ethylene and propylene with acrylic acid, acrylonitrile and acrylamide degrades under soil burial. Acrylamide is this polymer this is water soluble polymer. This acrylamide, this monomer, this portion can be copolymerized with ethylene or other vinyl monomers, or we can have polyalkyl cyanoacrylates, say polyisobutyl cyanoacrylates, polymethyl cyanoacrylate. We can have polymers of say acrylic acid and acrylonitrile. So, these polymers degrade slowly by microorganisms or hydrolytic degradation. Cross-linked poly 2 hydroxyethyl methacrylate hydrogel hydrolyzes in vitro. Now, this is actually this poly 2 hydroxyethyl methacrylate, this is known as polyhema. If there is hydroxymethyl group, this is called polyhema. Hydroxyethyl, oh sorry, should write this way, polyhema, HEMA, polyhydroxyethyl methacrylate. Polyhydroxyethyl methacrylate is polyhema. This polyhema, this is a very good biomedical polymer. This is used to make contact lens along with other acrylic monomer. So, a copolymer of some other acrylic monomer and this polyhema and other hydroxyethyl methacrylate copolymer of hydroxyethyl methacrylate and acrylic monomer forms good contact lens which can be very extended wear and soft contact lens, which provides facility of water and oxygen permeability. Now, this cross-linked polyhema is a very good hydrogel. This cross-linked polyhema is a very good hydrogel and that hydrogel can be used for drug delivery device also. Modes of biodegradation are by microorganisms, fungi, bacteria, enzymatic degradation where physical factors affects the activity of enzymes, degradation by biological oxidation, degradation by biological hydrolysis. So, all these three are influenced by enzymes, whereas these fungi and bacteria can also degrade polymers. This shows a chemical scheme, reaction scheme for enzymatic hydrolysis of starch and cellulose. This is the anhydrous glucose unit of starch or cellulose. Now, enzyme in water that breaks this linkage forming fragments, that means the molecular weight of these polymers is almost reduced to half if there is one action of enzyme at this bond. Similarly, more action of enzymes can fragment a cellulose molecule or starch molecule to many such numbers of this anhydrous glucose units with hydroxyl groups at one end. So, this way we can degrade the starch and cellulose polymers. And biological oxidation and hydrolysis by enzymes, this shows a scheme of reaction that is basically this is an oxidation process. This oxidation reaction is catalyzed by the presence of enzymes and it actually produces ultimately acids and alcohols if the polymer is a polyester. So, this degradation of polyesters by the action of enzyme, basically it is oxidative process, enzymatic oxidation process that produces fragments containing acids and alcohol groups. So, the products will become acidic in nature. Now, polymers can also be converted to biodegradable, non-biodegradable to biodegradable nature through chemical modification. Say polymers with carbon chain backbone except for those with larger number of polar groups on the main chain such as PP are not susceptible to enzyme catalyzed degradation reactions. In this connection, we can discuss that say LDP films which are used as packaging films, as carry bag films, which are creating a lot of nuisance in the environment. These films are flying here and there, littering here and there on the roadside or on the garbage side. So, which is actually creating a lot of nuisance and problems in the environment to the society also. So, this we cannot avoid the use of such LDP films as packaging films or carry bags, we cannot avoid, we have to use, but we must think of certain process which can degrade these films, carry back films after it is thrown to the garbage. Now, as I mentioned, the surface energy of these polymers are such that the contact angle is very high, the bacteria cannot sit on the surfaces, but if the surface of such LDP films can be made polar, means the oxygenation, this can be oxidized by some means, So, some oxygenated groups like say OH group or ketonic group or ether group or ester group, etc., if these could be created on the surface of this LDP by any means through oxidation, by means of oxidation, then such LDP can be degraded by microorganisms. So, that is a kind of modification. So, if this LDP can be exposed to corona, high voltage corona, say air corona. So, that air contains oxygen, a high oxygenated highly active oxygenated species will impinge on the LDP surface, and this LDP surface will be oxidized. That oxidized LDP surface can be degraded by microorganisms or bacteria as well as fungi. That is possible. We have done some experiments, we have seen that yes, it is working, it is functioning. So, that technology can be developed. So, there are two approaches for modification of such polymers: insertion of functional groups in the main chain, especially ester groups as I mentioned, which can be cleaved by chemical hydrolysis, or insertion of functional groups in or on the main chain that can undergo photochemical chain cleavage reactions, typically carbonyl groups. This is done by free radical copolymerization with a special monomer that undergoes free radical ring opening reaction to generate a main chain ester group. So, there is possibility of converting non-degradable hydrocarbon type of polymers which will be degradable by microorganisms by chemical modification on their surface. So, here shows a reaction scheme which is basically insertion of some ester group onto a vinyl polymer like this. Here you see some ester group has been inserted in a vinyl polymer, and this vinyl polymer being hydrocarbon in nature, having only carbon-carbon backbone chain. Now, that has been converted to a carbon chain with some oxygen atom and ketonic group, the ester group on the backbone chain. So, COO has been inserted in the backbone chain. So, that vinyl polymer will be degradable by this process if it is modified. Similarly, ketone group can also be inserted in vinyl polymer, and here you see some CO group has been inserted by this way of chemical reaction, and such insertion of ketone group can also help degradation of vinyl polymers. Basically, as I mentioned that if a polymer surface can be oxygenated, means oxygen atoms in the form of ketone, ester, hydroxyl or ether, if such type of groups can be created on the surface of a polymer, that polymer will be degradable by hydrolysis or by microorganisms. Now, this again shows another kind of reaction scheme known as Norris 1 and Norris two reaction mechanism for the degradation of copolymers of ethylene. Now, this is one path and this is the now is two path, and ultimately these are the your fragmented products forming from a polyester molecule. We can get fragments having groups like carboxyl, an acidic group, as well hydroxyl group, alcohol group. So, a polyester bond after breaking it will form carboxyl and hydroxyl groups, and polymer chain will be fragmented into many parts. Then other ways and means of developing biodegradable polymers are by blending a non-degradable polymer with a degradable polymer. Say polyethylene is a non-degradable polymer and that can be degraded. This polyethylene polymer can be degraded by blending with starch. People have taken ventures today available. This kind of product is also available in the market. This polyethylene starch film or modified polymers can also be chemically modified polymers and starch can be blended to form some biodegradable polymers. Actually, agricultural mulch films are being produced from blending of polyethylene with starch. Now, the reasoning behind this approach of blending starch with polyethylene is that after degradation of the biodegradable component of the microorganism by microorganism, say if starch is incorporated there, starch is a very good excellent food for microbes. So, starch will be eaten which remains dispersed within the polymer film, and ultimately what happens, this your starch will be eaten up and the polymer film will be porous and it can be easily fragmented into smaller pieces, disintegrated into smaller pieces, and surface will be increased and this microorganism will degrade the film at a very faster rate. Now, without there are some LDP films which are used today for packaging. These are stabilized with some stabilizers, antioxidants, etc., that degrades at a very slow rate, say 2% per year, and spontaneous tearing of such film occurs after 10,000 hours of compost or degradation. Then degradation involves the oxidation of terminal methyl group followed by beta oxidation. This is the mechanism of degradation, how this stabilized LDP film degrades, but that is very slow process, and that is we cannot consider such type of stabilized films as degradable polymers. So, there are blend systems available and already which have been manufactured and products are available in the market. These are the systems: starch, glycerol, polyvinyl alcohol, which produce water soluble bags which have been developed. Starch LDP blend has been produced and patents have been taken on this process technology. 50% starch polyethylene co-acrylic acid polymer, acrylic acid ethylene copolymer with 50% starch, that also have shown very good degradation properties, and that has been used for packaging and agricultural mulch film. Gelatinized starch was also blended with ethylene acrylic acid copolymer for agricultural mulch application, as well as packaging. 40% starch in 20% ethyl acrylic ethylene coacrylic acid polymer and 25% LDP. So, LDP ethylene acrylic acid copolymer and starch. So, 40, 20, 25, 15% along with 50% urea, which are actually some fertilizer is also included in this film, which gives some slow release fertilizer action as well as degradation. This is for agricultural purpose. Starch LDP encapsulated urea film was also used for controlled release of fertilizer, controlled release fertilizer films for agricultural applications. Then polymers can also be modified for developing biodegradable polymers through copolymerization, graft copolymerization of thermoplastic polymers onto starch. So, starch can be grafted with say thermoplastic polymers. So, some works have been done and some patents have also been taken. Here is few examples. Starch was grafted with polymethyl acrylate, and starch was blended with polymers having reactive polar functional groups. Starch was blended with polymers which are already oxidized to some extent, say the oxidized polyethylene or LDP, which are blended with starch. So, after oxidation of polyethylene, this becomes little degradable and starch can be miscible with this thing, otherwise starch is difficult to mix with polyethylene. That is why oxidized polyethylene was used for blending with starch, and blends of starch, styrene, maleic anhydride copolymer, that was also used or developed for making preparing biodegradable films. And for the application of biodegradable polymers, we can mention the surgical sutures. So, most popular absorbable sutures are polyglycolide PGA, poly-L-lactide PLA and their copolymers. These are used as very good bioabsorbable sutures. Bone fixation devices, say these bone fixation devices are made from polyglycolic acid, polylactic acid and polydioxanone along with other materials. Vascular grafts made from cross-linked gelatin heparin complex. Adhesion prevention was also used during surgery. These are photocurable mucopolysaccharides which are used. Artificial skin was made from collagen, chitin and poly-L-leucine, also collagen from fish scale, that can also be used for artificial skin. Drug delivery system, say polylactic acid and polyorthoesters are used for as drug delivery systems, and other applications, agricultural mulches, already I have mentioned, controlled release of agricultural chemicals like say fertilizers and other pesticides. Those are also can be incorporated in polymer for slow release. Agricultural planting containers, say sapling pots etc., have been also developed. Packaging films with polyhydroxybutyrate, covalent, starch, purulane and chitosan films for food packaging. LDP blends with 10% cornstarch made into bags for groceries or rubbish films. And conclusion, essential guidelines to reach the goal of biodegradability is selection of a suitable polymer class, engineering essential structural units in the polymer, easy access of the polymer to the biodegradation agencies by the development of appropriate polymer texture having more exposed surface accessible to the degrading agencies, creating accelerated biodegradation environment and chemical modification of commodity polymers for biodegradation. Thank you.